The Euler equations gave us the estimations of theoretical head of a centrifugal pump. And by assuming that at the inlet we have no whirl at the inlet, that means no real components at the inlet, we can assume that the tangential components at the inlet of the absolute velocity is equal to 0. We can write down the Euler equations only as the outlet part of the pump. And then we also know from the velocity triangle at the outlet that the tangential components of the absolute velocity, or Cx2, is equal to u2 minus to the relative velocity, the tangential components of the relative velocity, or wx2. And by working on the angle, or the blade angle at the outlet, we can get the wx2 as a function of the radial component of the absolute velocity multiplied with the cotangent of beta 2. And then CR2 can be derived from Q, or the flow rate, and the area of the blade. And then combining these two equations, then we know that Cx2 is equal to U2 minus Q per A multiplied with cotangent B and A. We put it back to the Euler equations. We get this form as equations. And as we know that A and U and beta 2 will remain constants, we can replace them with K1 and K2 and Q. And this is the base for us to make a plot of the pump characteristic curve. So the line 1 is based on these equations, and due to slips we will add the slip factor into it, and then we will get the pump characteristic curve number 2. If we consider let's say a shock phenomenon due to the fluid interactions within the pump, we will have the characteristic curve of number 3 here. So number 3 represents the shock conditions at the inlet of the impeller and due to frictions between the pump elements. On the other hand, the final form of the characteristic curve is represented by line 5. If we consider all of the sources of the losses and so on, so the line 5 is the final form of the characteristic curve if we plot them based on head and flow rate. So line 5 is the final form of the characteristic curve of a centrifugal pump.